So we're going to convert an integral to polar coordinates, 2x minus x squared, y root x squared plus y squared, dy dx. Okay, so we would think that it makes sense to convert this to polar coordinates because I see x squared plus y squared. I see more x squared in here. Usually that tells me polar coordinates can make things a little bit easier for me. And I have to remember that there's a couple different things to do. So I'll go ahead and write dr d theta for now. Maybe we have to change that. But while I'm thinking about it, I'm going to convert my f into polar coordinates. So x squared plus y squared becomes r squared. I keep doing this. So my dy dx became r dr d theta. We'll decide later if we need that. Square root x squared plus y squared just becomes square root r squared. So that's going to be an r. And then y becomes r sine theta. And I just need to figure out my bounds of integration. So for me, it usually helps to draw pictures. So let's do that. I know that my x goes from 0 to 2, so I'm thinking about this region of the xy plane, 0 out to some 2. And then my y starts at 0, so I know I'm not going below the x-axis, but my y goes up to root 2x minus x squared. That's y squared equals 2x minus x squared. That's y squared plus x squared minus 2x equals 0. And that's just like this thing we did earlier, but x and y have swapped places. Y squared plus x minus 1 squared equals 1. So I complete the squared. X squared minus 2x plus 1 is x minus 1 squared. So I add an extra 1 there. So that's a circle that's centered here and has radius 1. So this is my region. Cool. Oh, real quick, just like a word of warning. So some of you will think to do this. You'll think, okay, I know my rules for converting things. X becomes 2 cosine theta times r. Oops. None of you would write it that way. You would do r cosine theta and minus x squared, r squared cosine squared theta, or r squared minus y squared for r squared equals x squared plus y squared. Whatever you choose to do there, your bounds definitely depend on both r and theta, so that's no good as a bound for r or theta. So this idea to just start plugging substitutions into your bounds generally won't work out for you unless it's a very nice problem. So this drawing a picture and figuring out what's happening really is necessary. So how are we going to best represent this? My distance r is again seeming to change. So I'm going to need a function that tells me r in terms of theta for that top of the circle again. So I'm going to go ahead and say if I need my r bound, I'm going to go back to this equation I found right here, y squared is 2x minus x squared. Is that going to help me out? Yep. Here, I've got this thing again. X squared plus y squared equals 2x. Should have gone one down maybe. That's r squared is equal to 2r cosine theta. Yep, cosine is adjacent. That's the Langlois one. So r is equal to 2 cosine theta. That tells me the top of this circle. And then I have to figure out my bounds for theta. So the easier one is the lower one. I definitely start on the x-axis. So my lower bound for theta is 0. But like, how far back do I spin? Because here it seems like I don't go back at all. But, you know, here it seems like I go back almost to the y-axis. And maybe a picture will help convince you that it is, the upper bound is pi over 2. I'm just going to write that first. And then if I zoom in to, if I zoom into a circle, which I draw really fast so that I hopefully get a mostly round. Okay. So here's x equals 0. Here's x equals 2, 1, 0. The like tangent to the circle, you know, up at the top is horizontal, over here is vertical, and over here is vertical. So there's like an instantaneous point right here, same time when r is for a second 0, we're no distance from the origin, where the amount that you have to rotate back from the x-axis for theta is actually to meet this vertical line. So it really is theta equals pi over 2. And so that's where I get that upper bound for theta. I know that's a little harder to see, but it's really hard to think about. Like, what you're doing is you're writing r is 2 cosine theta. So you start out here, and then you kind of like trace back on this circle. And then there's a split second where you're traveling from the origin is going straight up and down. And so that's why we do need that last theta at pi over 2. Actually, I'll leave those raised there. They look nice. Okay, I probably have time to evaluate this. 0 to pi over 2, 0 to 2 cosine theta. I think it was r sine theta, r d theta. dr d theta. Okay, cool. Oops, r dr d theta. Okay, so this is 0 to pi over 2, 0 to 2 cosine theta, r cubed sine theta, dr d theta. And so we're going to evaluate the innermost integral first. 0 to 2 cosine theta, r cubed sine theta with respect to r. So the sine theta may as well be a constant. So I'll go ahead and pull it out. And then r cubed becomes 1/4 r to the 4th, evaluated from 0 to 2 cosine theta. Oh, this looks like it's going to be unpleasant. So I'll pull my 1/4 out front all the way, integrate from 0 to pi over 2, sine theta, and then 2 cosine theta to the 4th becomes 4 cosine to the 4th theta. Sorry, 2 to the 4th should be 4 squared, so that's 16. 2 times 2 is 4. 4 times 4 is 16. Okay. Minus 0 to the fourth is 0. So I'm going to pull out that 16. I've got integral 0 to pi over 2, sine theta cosine to the fourth theta d theta. So I'm going to take u substitution, cosine theta du equal minus sine theta d theta. So this is minus 4 integral from 0 to, leave off my bounds until I'm done. The minus came from that minus. Like that. So that's minus 4 times integral of u to the fourth is 1/5 u to the fifth. Evaluated over its bounds. So minus 4 times 1/5 cosine to the fifth theta for theta from 0 to pi over 2. Minus 4/5 times, well, cosine pi over 2 is 0. So 0 to the fifth is still 0. And cosine 0 is 1. 1 to the fifth is still 1. So this just becomes 5. Not 5, 4/5. And if we go back to the beginning, we were finding the area of, we were evaluating this function over this area. So kind of if we had integrated with respect to y, we would have used a u sub to start, but then I think this did end up being a little bit easier just because we didn't have to deal with the x minus x squared inside a square root.